Hi, my name is Kenzie Gubler, and this PowerPoint is for Organic Chemistry 2310 at the University of Utah, and my organic molecule of societal interest is vancomycin. In 1953, while working for the pharmaceutical company Eli Lilly, Edmund Kornfeld isolated vancomycin from the soil of an island in Southeast Asia. Vancomycin is produced by a bacterium, Streptomyces aurantialis. Vancomycin is an example of a naturally occurring halogenated organic compound that is somewhat rare in most animals and plants. It's considered an organohalogen natural product. It became quickly apparent that Staphylococci did not develop significant resistance in a culture containing vancomycin. Very soon after its discovery in 1958, Eli Lilly marketed vancomycin under the trade name Vancomycin to treat several bacteria infections. It was named vancomycin from the word vanquished, and that's because of how effective it is and its multiple mechanisms it has against microbials. Some of vancomycin's properties include, well, it has a really large chemical formula, C66H75Cl2N9O24. That all adds up to a huge molecular weight of 1,449.27 grams per mole. Vancomycin is a branched tricyclic glycosylated peptide, and there's no conformer because there are way too many atoms present. Vancomycin works against gram-positive bacteria by inhibiting the production of the cell wall. Essentially, while the bacteria is trying to synthesize the cell wall, vancomycin does not allow the chains made by the bacteria to interact. As we saw previously, vancomycin is a very large and hydrophilic molecule. Because of this, vancomycin forms hydrogen bond interactions with the terminal amino acids. This stops the synthesis of the backbone strands of the bacterial cell wall that the bacteria is able to make when vancomycin is not present. Because of this, the cell wall falls apart. Gram-negative bacteria produces their cell wall in a different mechanism which does not allow vancomycin to penetrate their cell wall and therefore is not effective. Since it is such a large molecule, vancomycin is not absorbed systemically and is only used for localized treatment. It's administered as a short-term intermittent IV infusion for doses up to 1,500 milligrams, or as a 1.5 to 2 hour intermittent IV infusion for larger doses. Infusion rate-related side effects have been noted when shorter infusion times have been used. Short infusion times result in hives or intense skin flushing, which is known as breadman syndrome. The synthesis of vancomycin is really complex. We begin with what's on the left and attempt to add the two carbohydrate molecules that are located on top of the phenolic group of ring D, which is the one that's being pointed to on the left. In order to attach the carbohydrates onto the aglycan of vancomycin on the phenolic group of ring D, which once again is that group that's being pointed to by the arrow, we first need to protect it from any unwanted reactions. Obviously, there's lots of places and locations for reactions to take place on such a large molecule. So, to get the reaction we're wanting, we're going to be adding TBS OTF to 2, which is being represented by all of the R groups on that diagram you're seeing above. While doing that in the presence of 2,6-glutadine, after an aqueous workup, you get the TBS molecule, which is going to be our derivative 3. As you can see, now we have those TBSs that we just added from our last step. Exposure of TBS3 to excess CH2N2 in diethyl ether gave methyl ester 4, which led to the CBZ protected derivative 5 upon treatment with CBZCl and aqueous solution of NaHCO3. So now the TBS group on ring D can be removed by KFAL2O3 to the desired glycoside acceptor 6. As you can see, now we have the TBS that we just added in our last step. Exposure of TBS3 to excess diazomethane and diethyl ether gave methyl ester 4, which led to the CBZ protective derivative 5 upon treatment with CBZCl and aqueous solution of sodium bicarbonate. Now, the TBS group on ring D can be removed by potassium fluoride aluminum oxide to the desired glycoside acceptor 6, which we'll be seeing on the next slide. Once again, shown at the bottom of this slide is our product from the previous slide. And so the final reaction scheme to attach the disaccharide onto substrate 6 required several experiments and fine-tuning with protecting groups. Attempts were foiled by steric hindrance and unwanted reactions. First, this glucose-derived donor, 12, is reacted to attach onto the phenolic group of ring D. The second step follows with the vancomycin-derived donor, 13, including a fluoride activating group at C1. Our final reaction consists of removing the protective groups, which we have added, and that is done in a series of reactions to produce vancomycin. And that's the synthesis.